Hello, my name is Olivia and I am a current PhD student at the University of Cambridge and a member of Emmanuel College. I am part of the physics department and I would like to talk a bit today about the research I am doing for my PhD. I work on studying the light emitted from energetic reactions, or as I prefer to call it, looking at the colour of explosions. As I'm sure you're all aware, when explosives react, they do so violently, producing a lot of hot gas in a very short period of time. This produces a very high temperature and high pressure environment, conditions which are normally incredibly hard to create in a controlled manner. This gives me the chance to measure how the light is affected by such extreme conditions. However, I do have to be a bit more careful about destroying my own equipment than a lot of other scientists might be. Explosives can react in a lot of different ways, leading to a lot of different reaction regimes and conditions. Part of my research is focused on how the light changes as the reaction gets more violent. So starting with the less extreme reaction, this is burning. This occurs at room pressures and temperatures of a few hundred degrees Celsius. Explosives can be burned fairly easily over a Bunsen burner, in a way similar to how we might have done in old school chemistry lessons and flame tests. Now, looking around at everyday flames, such as in candles, you might notice that nearly all of them have exactly the same colour, that is, this distinct yellow-orange. And explosive flames are no different. This is because a sodium atom burns a lot brighter than any other atom that you will commonly see. And it is also incredibly common. Therefore, when you burn something, it is the small impurities of sodium which are dominating the spectrum, burning brighter than everything else, even in explosive flames. So going to the more extreme end of the scale is the reaction which is arguably the most well known, and that is detonation. In detonation, the reaction spreads through the material faster than the speed of sound, producing a shockwave. In my materials and experiments, I measure speeds of 7,000 meters a second, accompanied by temperatures of around 8,000 Celsius and pressures 100,000 times greater than what we would have in our normal atmosphere. Looking specifically at the light, it is no longer due to the sodium impurities. Similar to how metal, when heated up, goes red and then white, the light I see is due to the temperature of the reaction. And from the light and the colour of it, I could work back and measure that the reaction was at 8,000 Celsius. Now, going in between burning and detonation, there are a lot of different reactions which all fall under the category of deflagration. In a typical deflagration reaction, temperatures are a lot cooler, with only 4,000 degrees Celsius, and pressures of 5,000 times greater than the normal atmosphere. Still pretty hot, and so some of the light is due to this temperature. However, I also see the sodium impurities, so in many ways it is completely like an in-between reaction between burning and detonation. By changing the initial setup of the experiment and conditions, I can see how the light changes, and from that I can see how the temperature and indeed pressure of the reaction changes. In this sense, just by looking at the light, I can gain an understanding of how the materials change under high pressures and temperatures of quite a large range of conditions. Once this is understood, the underlying physical laws and rules can be applied to a wide range of disciplines, from astronomy to combustion science, to allow the measurement of properties of many high-pressure systems.